Hey everybody, welcome to Kung Fu Physics. We are solving practice physics GRE problems one at a time. I'm running way behind today, so it's going to be a quick one. And the one I want to look at is number 100 off of the 1992 exam. So if you've got those at home, pick it up. 92 exam, number 100. Looks something like this. Got a picture and everything. So this is just a classical mechanics problem, a statics problem specifically, I would say. It's a really easy problem if you set it up right. I was just monkeying around. I hadn't looked at the solution for this one or anything, and so I was just monkeying around with this. Kind of solving it the way I would if I was back in freshman physics, and found myself going down some dead ends as far as the solution's concerned, wasting a ton of time on this one. And that's a shame, because if I was actually doing this on the physics GRE, this is easily within the grasp of knocking this out in a couple of minutes and getting a point off of this problem. So I don't know what to say about that, but I guess my advice is keep in mind that these problems are designed to be solved in a couple of minutes. So if you start doing something that is more difficult to you than what you are thinking should be done in a couple of minutes, then you're going about it the wrong way, and you need to abandon that approach as soon as possible for a better approach. Because all of these are designed to be done in a couple of minutes. So in other words, if you have a problem and you're just hacking through this and you're like, this is the hardest problem, I can't believe it's on the physics GRE, this will take me a half hour to do, then you're doing it wrong, and there's got to be another way to do it. There's always many ways to solve problems. Maybe not always, but almost all of the time there's more than one way to solve something like a physics problem. So if it's taking too long, abandon it and go about it another way. So let's not waste any more time. Let's go ahead and get started on this one. I would scan the answers quickly. The only thing that would jump out there, obviously all the answers are distances in meters. The only thing that jumps out at me right off the bat is there's a 0 in there, which I may be able to eliminate quickly or choose as an answer quickly if that happens to be the case. And so I would just scan those answers and then move on to the problem, take a quick glance at maybe the picture, and then I would go ahead. Number 100. A uniform rod of length 10 meters and mass 20 kilograms is balanced on a fulcrum with a 40 kilogram mass on one end of the rod and a 20 kilogram mass on the other end, as shown above. How far is the fulcrum located from the center of the rod? Okay. So this is, as I said, a statics problem, and you probably remember doing a lot of these in freshman physics, and it involved summing the moments and setting them equal to 0. I think I do it a little bit different than most people, but I really do prefer my way of thinking about it, so I'm going to go ahead with that. So I draw on my diagram here the fulcrum and this bar, and then that's where we're going to be adding those two masses to the ends, and they are the forces. I'm going to leave off the units of kilograms, and the forces would be 20g, where g is the acceleration due to gravity, and 40g on the end there, because that's a force. Now there's also, the whole trick to this problem is recognizing that there are several ways to set it up, and that's where I was getting screwed up, is I was setting this up as 4 moments, and it worked. I solved the problem, but it took way too long. I was setting up a moment caused by this portion of the pole and a moment caused by this portion of the pole, and I ended up with just a bunch of junk. It all canceled up in the end, but it wasted me a lot of time. So what I would say as the correct way to do the problem is to just look at this as 3 moments acting on this fulcrum. 1, 2, and then the third one is at the center of mass of that pole. So we definitely do have a third. If we leave that off, we're going to screw ourselves up. But the center of mass of the pole is important, where you're taking the whole weight of the entire pole and you're having it act at its center of mass, which is right in the center. Okay, so what I want to do to set this up is take my distance from the center. I'm just going to call that D. I'm going to take my distance from the center of mass to the fulcrum. The center of mass of the pole to the fulcrum is my distance D. And that's what really helps you solve this problem, because that is what you're looking for in the answer. So, okay, blah, blah, blah. I'm taking too much time. We got to get moving on this. So we sum the moments. And the way that I look at it is I look at everything that's causing a moment this way, and I set it equal to everything that's causing a rotation, a moment, or a rotation that way. And so I've got two that are acting this way. I've got the total mass of the pole, and I need to get that. It says that the length is 10 meters, and the mass is 20 kilograms. So the total is going to be 20 kilograms. 20 G is going to be that force as well, acting there. So I've got 20 G acting at a distance D, and then this distance here, what is this? This is half of the pole, and the entire pole is 10, so this is going to be a distance of 5. So I'm going to add a force of another force of 20 G acting at a distance of 5 plus D, and then I'm going to set that equal to the force, the moment that's acting over here. Now this is going to be 5 minus D, right? So I've got a force of 40 G acting at 5 minus D. Okay, and even in my head, I'll do it on paper here, but on the whiteboard here, you're going to drop that G off quickly because it's on both sides. And honestly, if you can save yourself a couple of moments by realizing that's the case before you're even writing G, then do it. In your head, you're imagining the G there, but if you don't even have to write it, you're going to get the problem right if you can cancel that out from both sides. So by all means, take a shortcut there if you can. So just do an algebra at this point. I'm just going to try and blaze through this as fast as I can without looking like an idiot and messing up my algebra. Get 80D on this side equal to 100. D equals 100 over 80 equals 10 over 8, and then I could just do 8 into 10, and that's gonna give me the answer, right? Better. Yeah, that'll give me 1.25, and that's gonna be the answer that I'm looking at. You can get there without doing the long division. I'm sure most of you, some of you at least, can get there without doing the long division. So 1.25 meters, does that make sense conceptually? Yeah, it does. I mean, after just reading the problem quickly, you should be able to eliminate 0 because if the fulcrum was right at the center, sure, that would work out fine for the mass, the rod. The rod would balance fine, but if I'm putting two unequal weights equal distances away, then certainly it's not going to be 0. We could have eliminated that early on. I guess there's no other way for me to say readily, of course it's not this or that other answer, but if we've done this and we're confident in our work and we did it right, then we should have no problem there going ahead and picking answer C, 1.25 meters as our answer, and moving on to the next problem. So I guess, like I said, that's a pretty easy problem to do. If you set it upright, I think you could do it in a couple minutes or less if you set it upright and knew exactly what you were doing. So practice hard, and I'll see you next time.